In this screencast, I'm going to talk about a common joint probability mass function known as the multinomial distribution, which is an extension of the binomial distribution. Before we get started, I have a review question that's going to help us understand the multinomial distribution. How many arrangements can we make of 5 M&Ms where 2 of those M&Ms are blue, 1 is red, and 2 are yellow? This is a permutation of like or similar objects. We have a total n of 5 M&Ms where we've subdivided that 5 into n1. This is going to be blue. We have 2 of those. We have 1 red M&M and we have 2 yellow M&Ms. The number of ways that you can arrange this, permutations of similar objects, is n factorial divided by n1 factorial divided by n2 factorial divided by n3 factorial, which equals 5 factorial divided by 2 factorial divided by 1 factorial divided by 2 factorial. And when you do the math, there are 30 ways to do this. So this is going to help us in a minute when we derive the multinomial distribution. The multinomial distribution is going to allow us to solve this problem in a certain large bag of M&Ms. Large meaning if we remove a couple of M&Ms, it's not going to significantly alter the background probability, but 20% of the M&Ms are blue, 30% are red, and 50% are yellow. We're going to use the multinomial distribution to answer the question, what is the probability that if we choose 5 M&Ms at random, we will get 2 blue, 1 red, and 2 yellow M&Ms. So let's take a look at the multinomial distribution. And again, this is a common joint distribution. It's an extension of the binomial distribution. The result from each trial is not just pass-fail, but it can be categorized into one of k classes. In our question here, we have 3 different classes. M&Ms are not just red and yellow, but we have blue, red, and yellow. So we actually have 3 classes in this example. The probability of getting a result in class I is pi, and the trials are independent, meaning that the results of any trial are not significantly affecting the results of another trial. And again, in our example, we're assuming that we have a very large bag of M&Ms, so when you withdraw an M&M, it doesn't significantly alter the probability of the different colored M&Ms. So let's go through how we might derive this. What's the probability that we choose 5 M&Ms at random and we get 2 blue, 1 red, and 2 yellow? Well, one possible arrangement would be yellow, blue, red, yellow, blue. So that's a possibility. What is the probability of getting exactly this arrangement if order matters? The probability of getting this arrangement would be the probability of yellow squared, because we have 2 of those, times the probability of getting a blue M&M squared, times the probability of getting a red M&M raised to the 1, since we only have 1 M&M that is red. But there are lots of different ways to come up with this arrangement. In fact, related to the original question at the beginning of this screencast, if we refer to the number of blue as x1, the number of red as x2, and the number of yellow as x3, it turns out that the possible number of arrangements of these 5 M&Ms when we have similar or like objects is n factorial divided by x1 factorial divided by x2 factorial divided by x3 factorial. This here is the number of permutations of like objects. So what we end up doing for the multinomial distribution is we take that factor, the total number of permutations of similar objects, and then we multiply by the product of each individual probability of success for those k different classes raised to the number, the x1, the number of those successes that we are interested in. N here is just the sum of all of our xi's, and the sum of all the probabilities of our k classes has to equal 1. By the way, if you looked at the marginal distribution of any xi, it's going to be binomial, meaning that if you kind of average out or integrate out all of the others other than xi, it's going to follow binomial distribution, because now all you're looking at is a probability of success, and a probability of failure is anything else. Let's go ahead and solve this. If we plug these values into the multinomial distribution, we end up with the following equation, and when we do the math, we end up with about a 9%. So there's a 9% chance that If we take a random selection of 5 M&Ms, we're going to get 2 blue, 1 red, and 2 yellow M&Ms. So now I want you to try to answer this question, and I'll help you along with a couple of questions. Acme, a company that makes everything, produces widgets. 45% of those widgets are manufactured in China, 30% are manufactured in Korea, and 25% are produced in Mexico. What's the probability that in a sample of 10 widgets, at least 4 of them were made in China and at least 4 of them were made in Mexico? So to help you out, which of these possibilities satisfy the constraint that at least 4 of them have to have been made in China and at least 4 of them were made in Mexico? So given the answer to that question, what's the probability then, and you can do the calculations, that at least 4 of them were made in China and at least 4 of them were made in Mexico? Hopefully this screencast gave you a better idea of the multinomial distribution. Thanks for watching.